Hello friends, our topic is vector space. First, two important things of vector space are internal composition and external composition. At first, let's say internal composition. Let V be any set such that this is mapping R cross R to R and a function, okay? Then this is said to be internal composition and it also called vector addition. In external composition, let V and F be any two non-empty set. Then the mapping will be this one. In internal composition mapping, here 2 will be vector, and in external composition mapping one vector and one field element. Okay, field means scalar. This is said to be external composition. The other name of external composition is scalar multiplication. Okay, this external composition is in V over field F. Next, vector space, important things. Let F just a field and is plus and this dot represent multiplication and this plus represent addition. The elements of F will be called scalars. Let V be a non-empty set whose elements will be called vectors. Then V is a vector space over the field F. If there is defined an internal composition in V called addition of vectors. We already know that the other name of internal composition is vector addition, just it, and is denoted by plus, okay, because it's addition. Also for this composition, V is an abelian group. Okay, for satisfy the vector space, actually we have to prove these properties. Okay, condition for vector space. So just divide. I just divide in three parts. This one part A to E, and this is the second part, and this is the third part. Okay, third part. Okay, let's see. Condition for vector space. Alpha plus beta belongs to V for all alpha comma beta belongs to V. This is represent closure property. If alpha and beta are the element of V, vector space V, then alpha plus beta also belongs to V, and alpha plus beta equal to beta plus alpha for all alpha comma beta belongs to V. This represents commutative property, and this one associativity. Alpha plus beta plus gamma equal to alpha plus beta plus gamma. You already know it's called associative property. For an element 0, okay, and 0 just represent a vector element, okay, so it's belong to vector. This 0 actually 0 vector, okay, this will be called 0 vector, okay, and this is identity element, so alpha plus 0 equal to actually 0 vector is alpha plus 0 equal to alpha, okay, this show identity, okay. After that, to every vector alpha belongs to V, there exists a vector called minus alpha belongs to V, such that alpha plus minus alpha equal to 0. If alpha is an element of V, vector space V, then also a element minus alpha exists in vector space V, and such that alpha plus minus alpha equal to 0 is called inverse property, okay. Okay, second part. There is an external, the first part for internal composition, second part for external composition, okay. Second part, okay, let's see. There is an external composition in V over F called scalar multiplication, okay, scalar multiplication, because A belongs to F, and alpha belongs to V. Scalar element, okay, it's scalar multiplication, just nothing. In other words, V is called close with respect to scalar multiplication. This is close because A alpha belongs to F. The third one just the two composition, okay, the two composition here, okay. We just use internal and external both composition here and make this condition. First, A alpha plus, sorry, it will be beta, equal to A alpha plus A beta. For all A belongs to F and alpha comma beta belongs to V. And wait one second. Yes, and alpha plus and A plus B alpha equal to A alpha plus B alpha. For all A comma B belongs to F and alpha belongs to V. AV into alpha equal to A into B alpha, okay. Just scalar associative property here, just like addition. And for all A comma B belongs to F and alpha belongs to V, okay. Just A, B, just scalar element, okay, just scalar element of field F, and alpha beta the vectors in the vector space V, okay. And 1 cross 1 into alpha equal to alpha, and alpha belongs to V. Here I is the, that means 1 or I, actually it's just identity property, okay. So I is the unit element of field F. But this the all on condition. If all the condition will satisfy, after that we can say this is a vector space, okay. So thank you for watching. If you like, please like, share and subscribe. Thank you.